Hello everyone, welcome to SHR Trinity. Welcome back to the Generative AI Interview Questions series by SHR Trinity. In this part, we continue our journey through the most important generative AI interview questions frequently asked in technical interviews. In this video, we focus on concepts that are highly relevant for AI engineers, machine learning engineers, data scientists, software developers, and generative AI professionals. Each topic will be explained with practical examples, visual diagrams, architecture discussions, comparison tables, and interview-focused insights. Before we begin, subscribe to SHR Trinity and hit the bell icon so you never miss any updates from our end. Now let's continue with today's questions. We are also excited to announce the Generative AI Comprehensive Hands-On Training Program by SHR Trinity. This is a 30-hour intensive course featuring 20 live sessions of 1.5 hours each, held Monday to Friday from 7:30 p.m. to 9 p.m. The program commencement date is May 11, 2026. The curriculum covers foundational concepts of AI, machine learning, and deep learning, moving into LLMs, local GPT-2 deployments, prompt engineering, RAG pipelines, autonomous crew AI agents, Langflow workflows, and model context protocol. The course fee is 15,000 rupees. To enroll or learn more, contact us at contact@shrtrinity.io or call us at +91 70956 78789. In this module, we will explore the core architectural designs that make modern generative AI possible. We will explain the famous transformer architecture, define self-attention and multi-head attention mechanisms, review positional encodings, compare encoder versus decoder frameworks, and detail how GPT models generate text. We will wrap up with critical concepts like tokenization, vector embeddings, and context window limitations. Question 11. What is transformer architecture? Introduced by Google researchers in their historic 2017 paper titled "Attention is All You Need," the transformer is a deep learning architecture that completely replaced recurrent neural networks, or RNNs, and long short-term memory networks, or LSTMs, for sequence modeling. Unlike RNNs that process text sequentially word by word, transformers process the entire sequence of tokens simultaneously in parallel. This massive parallelization allows models to train on internet-scale datasets using modern GPU clusters. The core engine of the transformer is the self-attention mechanism, which allows tokens to look at other tokens in a sentence and calculate contextual relationships regardless of their distance. A standard transformer consists of an encoder stack that extracts features from input sequences and a decoder stack that generates output sequences. Question 12. What is self-attention? Self-attention is the key mechanism within the transformer that enables a model to focus on the most relevant parts of an input sequence when processing a specific word. For every input token, the model projects its embedding into three vectors: a query vector, a key vector, and a value vector. To calculate how much attention a word should pay to every other word, the model takes the dot product of the query vector of the current word with the key vectors of all words in the sequence. These raw scores are scaled by the square root of the key dimension to prevent gradient issues, passed through a softmax function to turn them into probabilities, and multiplied by the value vectors. The result is a weighted sum that represents the contextual meaning of the token. For example, in the sentence "The bank of the river has a bank," self-attention helps the model differentiate between the land bank and the financial bank based on surrounding words. Question 13. What is multi-head attention? Multi-head attention is an extension of the self-attention mechanism. Instead of performing a single attention operation across the entire dimension of queries, keys, and values, the model splits these dimensions into multiple smaller subspaces, creating several attention heads. Each head runs its own self-attention calculations in parallel on these distinct subspaces. This allows the model to focus on different aspects of relationships simultaneously. For instance, one attention head might focus on subject-verb agreement, another head might look for pronoun associations, and a third head might track temporal relationships. The output vectors from all these parallel heads are concatenated together and projected through a linear layer back into the model's base dimension, creating a highly rich representation of the text. Question 14. What is positional encoding? Because the transformer architecture processes all tokens in a sequence simultaneously in parallel, it lacks inherent knowledge of word order. To a raw transformer, the sentence, "not bad, but good," looks identical to "not good, but bad." To resolve this, we must inject information about the position of each word in the sequence. Positional encoding achieves this by generating a unique position vector for each token location. These vectors are constructed using sine and cosine functions of varying frequencies, allowing the model to learn relative distance patterns. This position vector is added directly to the token embedding vector. By adding these values, the model can preserve the word order and sequential structure of the sentence during parallel GPU processing. Question 15. Encoder versus decoder architecture. Look at the comparison table. Standard transformers consist of two parts, but modern architectures often use just one. Encoder-only models, like BERT, use bidirectional attention, meaning every token can look at all other tokens in the sequence, both before and after it. This makes them ideal for understanding tasks, such as sentiment classification or named entity recognition. Decoder-only models, like the GPT family, use causal masked self-attention. This prevents the model from looking at future tokens, ensuring it only learns to predict the next word based on preceding text. Decoders are the standard choice for text generation and conversational systems. Question 16. What is GPT? GPT stands for Generative Pre-trained Transformer, developed by OpenAI. It is a family of large language models built strictly on the decoder-only stack of the transformer architecture. Generative means its main objective is to generate text. Pre-trained indicates it has completed self-supervised training on massive web text collections, learning vocabulary, syntax, reasoning, and world facts. Transformer highlights its reliance on self-attention layers. GPT models are scaled up to hundreds of billions of parameters, enabling them to generalize across diverse NLP tasks from translation to complex coding. Question 17. How does GPT generate text? GPT generates text using an autoregressive loop. When you send a prompt, the model processes the text and calculates a probability distribution over its entire vocabulary for the very next token. Using a sampling strategy like temperature or top P, the model selects a token. Temperature controls randomness. Higher values make outputs creative, while lower values make them deterministic. Once selected, this token is appended to the original prompt, and the updated sequence is fed back into the model to predict the next token. This recursive cycle continues until the model produces a special end-of-sequence token or hits a predefined length limit. Question 18. What are tokens and tokenization? Large language models do not read raw characters or text strings directly. Instead, they process numbers. Tokenization is the pre-processing step that breaks a string of text down into smaller units called tokens, and maps each token to a unique integer in the model's vocabulary list. Modern LLMs use subword tokenization, such as byte pair encoding, or BPE. Subword tokenization splits rare words into pieces while leaving common words intact, allowing the model to handle spelling variations and new words without throwing errors. As a rule of thumb, one token is approximately equal to 4 characters of English text, or 3/4 of a word. Question 19. What are embeddings? Vector embeddings represent the meaning of words, sentences, or documents as arrays of floating point numbers in a high-dimensional vector space. In this space, words with similar meanings are positioned close to one another. The mathematical relationships between these vectors capture semantic concepts. For example, if you take the vector for king, subtract the vector for man, and add the vector for woman, the resulting vector is mathematically closest to the vector for queen. Semantic similarity is measured by calculating the cosine angle between two vectors, which helps models determine how closely related two pieces of text are. Question 20. What is context window? The context window is the maximum amount of text a large language model can process in a single inference pass. This limit encompasses both your input prompt and the model's generated response. When a conversation exceeds this limit, the model must discard earlier parts of the chat, losing its memory of past messages. The primary bottleneck is the self-attention mechanism, which has a quadratic computational complexity. This means doubling the context length requires 4 times the computational power and memory. While older models were limited to 4,000 or 8,000 tokens, modern architectures use techniques like flash attention to handle over 1 million tokens. Thank you for watching. If you found this video useful, please subscribe to SHR Trinity for more videos, and click the like and share buttons. Stay tuned for part 3, where we will cover prompt engineering and AI application development. If you are interested in attending our live training sessions or have any inquiries, all our contact details are displayed right here on screen and are also available in the video description below. Feel free to reach out to us. We would love to have you as part of the SHR Trinity learning community. See you in the next video.